this is our module number 20, Electrochemistry. Our learning objectives are going to be to identify oxidation, reduction, oxidizing agent, and reducing agent as a chemical equation. And also you will be able to complete and balance redox equation using the method of half-reaction. So electrochemistry is the study of the relationship between electricity and chemical reactions. It includes the study of both spontaneous and non-spontaneous processes. So basically electrochemistry is that relationship between electricity, and remember that electricity is the transfer of electrons. So it's basically the study of those transfer of electrons in a chemical reaction. As a reminder, let's go to understand a little bit about the oxidation numbers. For elements, for example, all the elements has an oxidation number of 0. All of them have an oxidation number of 0. And remember that, for example, a hydrogen as an element is H2. So if you have found H2, the oxidation number for oxygen is 0, as well as oxygen. Oxygen exists as O2, so that's the element. The element of oxygen is O2, so the oxidation number for O2 is 0. For monoatomic ions, it will be the charge. If the ion is from family 1, the charge is +1, so the oxidation number also is +1. If it's from family 2, it's +2. All of the families 2 has a +2 charge, so that's also the oxidation number. For fluorine is -1. For oxygen is going to be -2. This is not the element, this is just the ion of oxygen as H2O. Okay, so in H2O that ion of oxygen and an ion is -2, unless it's a peroxide. When it's peroxide, the oxidation number of oxygen is -1. Hydrogen is going to be +1 unless it's a hydride. If it's a hydride, then it's -1, but most of the time hydrogen is +1. And the sum of the oxidation numbers equals the overall charge. If you have a compound that doesn't have a charge, it means that the overall charge is 0. But in other polyatomic ions, okay, it will be the overall charge of the contribution of each of the elements or ions that are part of that polyatomic ion. We're going to see a few examples in a minute. So the oxidation numbers, to keep track of what lose electrons and what gains them, we assign the oxidation numbers. If the oxidation number increases for an element, that element is oxidized. If the oxidation number decreases for an element, that element is reduced. So for example, you have zinc plus HCl producing zinc chloride plus hydrogen. Here we have the zinc, that is an element, the oxidation number is 0. Here in HCl, remember that HCl is a strong acid, so it will be dissociated. So it will be H positive, H +1, the hydrogen. And this will react and produce this product. So zinc here is +2, and hydrogen here is 0. Remember that this is the element of hydrogen. It will exist as H2. So for this one, the oxidation number is 0. So zinc went from 0 to +2, and hydrogen went from +1 to 0. This number decreased from +1 to 0, so hydrogen was reduced, while zinc went from 0 to +2, so zinc was oxidized. A species is oxidized when it loses electrons. So zinc loses 2 electrons, that's why it's +2, because each electron is -1. So it went from 0 to +2, that means that it released 2 electrons. While hydrogen received 1 electron, okay, and because of that, it was reduced from +1 to 0. and in that way, that hydrogen gained those electrons. Now, an oxidation agent causes something else to be oxidized, while a reducing agent causes something else to be reduced. So if he reduced another compound, he was oxidized, okay, because he must release electrons to the other element or compound to regain those electrons. Okay, so here the zinc released those electrons and hydrogen received those electrons. So because hydrogen was reduced, the zinc is the reducing agent. And on the other hand, hydrogen received those electrons from the zinc. So he was reduced, but he oxidized zinc. So that's why hydrogen is the oxidizing agent. Okay, he was reduced, but he was the oxidizing agent because he was the one that accept those electrons from the zinc that was reduced. Most of the time, when we're talking about the reduction and oxidation reaction, we use the half reactions. The oxidation and reductions are written and balanced separately. We will use them to balance a redox reaction. For example, when 10 plus 2 and iron plus 3 react, we have this. First, zinc plus 2 will be transformed to 10 plus 4. So here, the zinc was oxidized because it increased that oxidation number from plus 2 to plus 4. And to do that, he must release 2 electrons. Okay, so most of the time in a half reaction of oxidation, you're going to see the electron as a product. Another way, for iron, 2 iron plus 3 will receive 2 electrons and we produce 2 iron plus 2. So the iron went from plus 3 to plus 2. So it was reduced, okay? Because went from plus oxidation number of plus 3 to the oxidation number of plus 2, it received 2 electrons. In the half reaction of the reduction, you're going to see the electrons in the reactants. In the half reaction of the oxidation, you're going to see the electrons in the products. Okay, so here the tin is the reduction agent and the iron plus 3 is the oxidation agent. Now, how can we balance a redox equation? For do this, we use the half reactions method. First, we need to make the two halves reaction. We need to identify which one is reducing and which one is oxidizing. Okay, so and then we separate both half reactions. Then we balance atoms other than oxygen and hydrogen. So we first balance the other elements different from oxygen and hydrogen, and then we balance oxygen and hydrogen by using water and protons. That's the way we're going to balance oxygens and hydrogen, and in that order. Other atoms different from oxygen and hydrogen, oxygen and then hydrogen. Then we're going to add electrons to balance charges. We're going to multiply by a common factor to make the electrons in half reactions equals. And we're going to add both of the half reaction to create our redox balance reaction. Finally, we're going to simplify by a common factor or converting hydrogen to OH if the solution was a basic solution. So in other words, and finally we're going to double check, the atoms and charges balance. So we have here basically the balance of other atoms, then the oxygen, then hydrogen, and then the electrons. And that's basically the 4 steps that we need to do in a way to balance a redox reaction. So let's see this example. We're going to see the reaction between permanganate and oxalate. Here we have the reaction, permanganate plus oxalate is going to produce manganese plus carbon dioxide. So first, what we're going to do is to identify which half reaction is which one is the reduction and which one is the oxidation. One is gonna be the permanganate with producing the manganese, and the other half reaction is gonna be the oxalate producing the carbon dioxide. Okay, so we're going to have those two half reactions, permanganate producing manganese and the oxalate producing carbon dioxide. Now we need to identify which one is which. So for example, let's work first with permanganate. In permanganate, we're going to look for the oxidation number of permanganate plus the oxidation number of oxygen is going to be equal to -1. This -1 is due to the contribution of both atoms for manganese and oxygen. Okay, so this -1 is not of oxygen, neither of manganese, is of permanganate. So this is the result of the contribution of both oxidation number for both elements. So that means that the oxidation number of manganese plus the oxidation number of oxygen is going to be -1. So for manganese, we don't know that oxidation number. For oxygen, we know that is -2 for each oxygen, and we have 4. So that means that is 4 times -2 is -8. So x minus 8 is going to be equal to -1. This is the total the total charge of the polyatomic ion. So now we can solve for x, and x is going to be equal to -1 plus 8. So x is going to be +7. So that means that the oxidation number of manganese in permanganate is +7. Now let's look for the carbon and the oxalate. Here, the same thing. We have the oxidation number of carbon plus the oxidation number of oxygen will produce a -2. Now here we have 2 carbons, and we're looking for the oxidation number of carbon. So that will be 2x. Okay, because we have 2 carbon. In this one, we just have 1 manganese, so that's why we use just the x. But here, we have 2 carbons, so we need to put 2x. We have 4 oxygen. Each oxygen is -2, so 4 times -2 is going to be -8, and is going to be -2 the charge of the polyatomic ion. So now we solve for x, so 2x is going to be equal to -2 plus 8. So 2x is going to be +6, and then x is going to be 6 divided by 2, okay? And x is going to be +3. So for carbon in oxalate, that carbon, the oxidation number is +3. So now we can see also that manganese went from +7 to +2. So that means that this half reaction, that is permanganate producing manganese, is the reduction because it was reduced from +7 to +2. So that means that the carbon was oxidized. That means that this number increased here. So let's see if that is true. So here we have a molecule, a compound. We don't see a charge here. So that means that the total charge is going to be 0. Okay? And the oxidation number of carbon plus the oxidation number of oxygen will be equal to 0. Oxygen is -2. So we have 2 oxygen. So it's going to be x -4. We just have 1 carbon. And x is going to be +4. So we see here that carbon went from +3 to +4, so carbon was oxidized. So this oxalate is basically the reduction agent, while the permanganate is the oxidation agent. So assigning oxidation numbers show that manganese is reduced from +7 to +2, and the carbon is oxidized from +3 to +4. So manganese permanganate is the oxidation agent, while the oxalate is the reducing agent. So let's work first with this half reaction, okay, and let's balance this half reaction. To balance the carbon, we need to add a coefficient of 2, okay? So the only things that we can add to balance half reaction are going to be coefficients. We can't add numbers here, okay, neither here. We need to add in front of the molecules or the ions. Okay, so here we have 2 carbons, here we have 1 carbon. So if we add a 2 in front of the CO2, we will have then 2 carbons. So that's what we're going to do here. Okay, so we add 2 carbon to a coefficient of 2 in front of carbon dioxide, and that will affect the carbon, but also will affect the oxygen. Okay, so here we have just 2 oxygen, and now we have here 4 oxygen because we add this coefficient in front of carbon dioxide. So that makes 2 carbons and 4 oxygen. So now we can see here in reactants that we also have 2 carbon and 4 oxygen. So basically we are balanced we have balanced the elements. But we have a difference in charge. We have here a -2, and we have here a 0. Okay, so we need to balance the charges. The only thing that we need to we are available to use for balanced charge are electrons. So we're going to add electrons, and if we're going to add electrons, that means that whatever we're going to add that in the reactants or the products, we're going to add negative charges. So if we add an electron in the reactant right now from -2, and if we're going to add, for example, one electron from -2, we're going to have a -3 here. Okay, well, if we add one electron in the reactant, so that is not gonna balance this one. So we have two charges, negative charge here. So we need to add two negative charge in this side. Okay, so that's why we need to add two electrons in the products. And remember, the carbon went from +3 to +4. So this was oxidized, and the electrons in the half reaction are going to be, for the oxidation, are going to be in the products. Okay, so that basically makes sense. Okay, so we have the electrons in the products because it's an oxidation half reaction. So we balance the charges, -2, total here and total here of -2. We have two carbons, for oxygen. So let's go to the reduction half reaction. Here, the manganese, we have 1 and we have 1, so we don't have to balance that element, but we need to balance now the oxygen. So to balance oxygen, we're going to use water. Water is H2O, so we have here 4 oxygens. So that means that we need to add 4 water in the products because we have the oxygen in the reactant. So we need to add those water in the products. So we're going to add 4 molecules of water to the products. And in that way, we have 1 manganese, 4 oxygen, and 4 oxygen. But now we have 8 hydrogens in the products. So because of that, we're going to add 8 protons to the reactant. And in this way, we can balance now these hydrogens in the reactant with those hydrogens in the products. So now we have 8 hydrogens in reactants. We have 8 hydrogens in product. We have 4 oxygen in products. We have 4 oxygen in reactant and 1 manganese and 1 manganese. Now, let's see the charges. Here we have a +8. Remember that we have 8 hydrogens protons. So we have +8 -1. This side is going to be +7, while this side is +2. So remember that the only thing that we have that we're available to add to balance charges are electrons. Electrons are negative charge. So if we have a +7 here and a +2 here, we may need to add those electrons in the reactant. And remember that in a reduction half reaction, always the electrons are going to be in the reactants. So we're going to add here, basically, we have +2, we have here +7, 5 electrons, okay? So we need to add those 5 electrons in the reactant, and now we have -5, -1 is -6, +8 is going to be +2. So this side is +2, and here we have a +2. So now we have all the atoms balance, all the charges balance. So let's combine both half reaction. We have here the half reaction, and also here this is the oxidation, and we have the reduction here. So to make the number of electrons equal on each side, we will multiply the first reaction by 5 and the second by 10, because even though we know that the electrons has been transferred, but electrons are not a reactant. You can have like 2 moles of electrons, so that's why they can be part of the final equation, even though they are the reason of why we have a reduction and oxidation reaction. Okay, but we need to cancel, we need to eliminate those electrons. So we have 5 electrons here, we have 2 here. We need to look to equals the number of electrons on both sides. So to do that, we multiply all the equation here by 2 and all this half reaction by 5. So that means that we're going to have 5 moles of oxalate producing 10 moles of carbon dioxide plus 10 electrons. This is for the uh, oxidation half reaction. And for the reduction half reaction, we're going to have 10 electrons. Remember that this is easy to identify because the electrons are in the reactant. So that's why this is the reduction half reaction. We have 16 hydrogen before we have basically 8. We have 2 permanganate, 2 manganese, and 8 water. Now we're gonna add these two equations, okay, to create the net equation. And it's gonna be something like this. All the reactants is gonna be in one side, all the products is gonna be in the other side. And now we have 10 electrons here, 10 electrons here, so we can cancel those electrons, okay, because we have both equals a number of electrons both sides, so we can cancel. And now we have something like this. We have 16 protons plus 2 permanganates producing 5 oxalate plus 5 oxalate producing 2 manganese plus 8 water plus 10 carbon dioxide. So this basically is the uh, redox reaction, okay, for permanganate and oxalate. And this is in an acid solution, okay? This is in an acid solution because we have protons here in the reactant. We verified that we have basically all the number of atoms. We have 16 hydrogens here, we have 16 hydrogens here, we have 2 manganese here, we have 2 manganese here, we have 10 carbon, 5 times 2, 10 carbons here, we have 10 carbon, 10 times 1 is 10 carbons, and oxygens we have 4 times 2, we have 8, 5 times 4, we have 20, so we have 28 total oxygens in the reactant. And here we have 10 times 2, 20 here, and 8 times 1, 8. So 20 plus 8, also we have 28. So we have balanced all the atoms. And charges, we have 16 plus, and we have 10 minus and 2 minus. So this will be 12. 16 was going to be plus 4. 2 times plus 2 is going to be plus 4. So basically we have balanced our equation. Sometimes we also can balance in basic solution, but this is pretty easy. So a reaction that occurs in basic solution can be balanced as if it occurred in acid. So if they ask for to balance in a basic solution, you're going to do the same thing that we did in the last example, okay? But at the end, once the equation is balanced, we're going to add OH, hydroxide ion, to each side to neutralize the protons in the equation and create water in its place. So because we are in a basic solution, we can't have protons neither in reactants or in the products, okay? So to do that, we add the same number of hydroxide as the number of protons. If this produces water on both sides, subtract water from each side so it appears on only one side of the equation. This is the same thing as with the electrons. So to do the balance of in a basic solution, let's use the same example that we have before with the permanganate and the oxalate here. This is basically the balance equation, okay, after we did all those steps to create this balance equation. And now we're going to add OH. Okay, we're going to add hydroxide. We have 16 protons, so we need to add 16 hydroxide in each side in the reactants and also in the products. So that means that 16 hydroxide will react with 16 protons to produce 16 molecules of water. We don't have hydrogen here, so we basically going to have 16 moles of hydroxide ion, and we are in a basic solution. So remember that OH is the basic species. So now we're going to have something like this. We're going to have 16 molecules of water because those 16 hydroxide react with these protons. And we're going to have also 16 hydroxide in the reactant. So remember that we need to add the same amount in each side in reactants and the products of hydroxide due to the number of protons that are in the equation. Now we see that we have water, molecules of water here, and also molecules of water here. So we can cancel this 8 molecules of water with 8 from here. We're going to left 8 molecules of water in the reactant, and our equation, balance equation in a basic solution will be something like this.